sir.
Okay, let's repeat now. So we have here now the temperature of a metal specimen weighing 350 grams. No? It is raised to 100 degrees Celsius. So this is this metal. No? We colored it red because it's red hot now. It's 100 degrees Celsius. No? Maybe we put it in a boiling water for so long that its temperature reaches 100 degrees Celsius. No? Its mass is 350 grams. We do not know what kind of metal is this. No? So therefore, since we do not know what kind of metal, we will determine its specific heat. No? So we call that specific heat value as C sub 1. No? I call it X because we do not know its value. Now, it must be, this one will be placed in a cold, not really cold water, but the water there is around 20 degrees Celsius. No? So the mass of the water in this container is 100 grams. No, 500 grams, no, the water. No? And no, its container, no, it is held by a copper container called calorimeter. No? The mass of the calorimeter is 100 grams. No? Now, the specific heat of calorimeter is provided in the problem. C sub 2, which we call as the specific heat of the calorimeter, is 0.93 no? Calorie per gram per degree Celsius. No? Now, what we do not have here is the specific heat of water. No? Now, if it is a liquid, no, the specific heat of a liquid, no, we can call it again, no, C3, no, which is basically the specific heat of water. No? The specific heat of water is a known value that's equals to 1 gram. No? Amo niyang values ng specific heat sa atong tubig. That's 1 calorie, 1 calorie per gram, no? Per degree Celsius. No? Or per Celsius degree, I think. No? So some text would give it as Celsius degree. No? Mr. Garcinilla, no, is always being admitted to the classroom. Hinay signal ni Mr. Garcinilla. Okay, so this is the specific heat of water. No? So the specific heat of calorimeter of the copper now is this one. No? Now, which of them do you think, when you mix all three of them, now which one will give off heat? No? Which will lose heat? No? Do you think there's a material that will give off heat? So I think the hotter material will be the one who will lose heat. No? So Q lost, no, will be due to the metal, no, that is at 100 degrees Celsius. No? So the value for heat loss, no, or heat, no, it's actually mass times specific heat, no, times its change in temperature. No? Now, usually, you know, in this case, no, the value of our mass here, no, is equal to, no, this is equals to 350 grams, no, times its specific heat, which is not known, no, which is unknown, and our temperature. No? So when they were mixed, when all of them were mixed together, no, you'll realize that from 20 degrees Celsius, no, which is the temperature of water and the container, no, nahimo siya kuno nga 25. No? Its temperature increases. No? This 350 grams, which is 100 degrees Celsius, lowers down to 25. No? So 25 is the combined, no, temperature of the three of them after we mix all of them. No? So the hot metal and the cold water and container, when they were mixed together, this is now their mixture temperature. No? So the relationship of that mixture temperature is, when we put it in our equation for heat loss, no, that will be 20. What? That's 100 minus 25. No? So although this is the final, this is the initial temperature, but for those who lose heat, no, that's initial minus the mixture temperature. No? So this will be 75, no, times 350 times x, no, and you'll have here, no, your heat loss. No? So the product of the three, if we combine all that, no, so we'll have 350 times 75, no, and we'll have something like a huge number that's 26,250, no, and we'll have a variable x. No? So this is our heat loss. No? Now, what is the one that will now gain heat? No? So heat gain, no, is created or is due, no, to the calorimeter container and the water below. No? So these two materials that are colder will be, no, the one who will increase their temperature. No? So heat gain is, no, again, heat due to, no, substance 2 plus, no, the heat gain by substance 3. No? So ano ning substance 2? The container, no? The calorimeter container. No? What's substance 3? This is the water. No? So therefore, no, if we'll try to find Q sub 2, so we need the, so if Q is mass, C, and then delta T, then this is equals, Q sub 2 will be 100, no? Times its specific heat. Specific heat of the calorimeter is 0.093. Its change in temperature is 25, no, minus 20, no. So for the colder material, which will gain heat, no, we will write the final mixture temperature minus the initial temperature. Notice the difference above, no. Above is, no, we write the initial minus the final because this one is losing heat, no. But for those who will gain heat, then the final minus the initial temperature. Now what will we add here? No? So we'll need to add, no, our Q3, no, which is the water. No? So our water is around, no, 500 grams. Its specific heat is 1 calorie per gram, no, per degree Celsius. And its change in temperature is the same, 25 minus 20. Question again, why 25 minus 20? Because they are in the same container. No? So their initial temperature will be the same. Their final temperature will also be the same. No? So how much is our Q gain? No? Q gain, again, no? There's an addition there. No? So how much will be our Q gain? No? So our Q gain is, kindly check now if I'm right. So this is now in calories, no? So this is the number of calories that our water and our calorimeter will receive. No? Now in our equation above, if Q loss happens to be equals to Q gain, no? Then we can write, no, 26,250, no, X will be equals to heat gain, which is 25,446, no, 0.5. No? And we'll see here that if we divide the two, no, so X will be, no, 2546, no, 0.5 divide by 26,250, no? And we'll have a value for our X, something like, no? How much is our X there?
0.97.
0.97.
97.
97, no? That's calorie per gram.
0.097, sir.
Ah,
0.097.
okay, 0.097, no? So that will be in this value, no? Okay, so this is the specific heat of the unknown specimen, no? So if there's a table listed there, I think we can look for the table and identify which or what metal is this. No? What metal is very near to this one. No? Now, this value is also very near to 0.093. No? So I believe it's either that this metal is also something like a copper metal. No, no, this hot metal above. No? The hot metal, after solving its specific heat, is very close to the specific heat of copper. No? But if there's such a material that will exactly fall to this value, then we'll be able to identify the material above. So one way to identify a metal is also by finding its specific heat. No? So specific heat is something like similar to density. No? Okay, do you follow? Huh? Any question from you?
None.
Okay, so
None,
this
sir.
is the methods of mixture. No? So we combine materials together, and now we will be proceeding to the next one below. No? So let's scroll this. No? And again, after this, I'll give you an activity for you to answer. No? Okay, so let me scroll this down. So, I think I'll erase this one. So are you done copying this?
Yes, sir.
So let me scroll this down. So we will now go into phase changes. Phase changes is about this is about another effect of heat. So we are going to find, guys. So our sample problem there is about a certain ice. So if you have a substance, water, at -5 degrees Celsius, it must be solid. Now, as you increase the temperature and make it reach 105 degrees Celsius, it will change from solid to liquid, then liquid to gas, and eventually into a steam. So there are different states of the substance here as we move it from one phase to another. So again, it is described in our Q1. Q1 is equivalent to the amount of heat needed to raise the temperature from -5 to 0 degrees Celsius. So Q1 is the heat that we use to increase the temperature. And how do we get the value of Q sub 1? So we know Q, guys, the very first equation of Q. Q is equivalent to M being mass, and then we multiply it to the change in the temperature. But we realize here that there's several changes in the temperature here. Now, this equation is true whenever there's a change in temperature. But you'll remember that we talk about also the latent heat. And in the case of latent heat, it's possible that in latent heat there's no change in temperature. So for our Q, for our heat, whenever the material is undergoing latent heat, then we have mass and we simply multiply it with L sub F. L sub F here is not anymore the final length. Our L sub F here is our latent heat of fusion. Now, another form of heat, guys, is latent heat of vaporization. So if we are dealing with latent heat of vaporization, then we are dealing with LV. LV is for latent heat of vaporization. Now, at different states also, the specific heat of the substance is also different. Now, in the case of water, so for water, again, no, water is liquid. No? The specific heat of the liquid water, we already know it earlier. This is equals to the one we call as C1, no? But we'll just call it CW. CW is for specific heat of water, and it's equals to 1 calorie, no? Per gram per Celsius degree. No? Amo na ba? Kayo na. But for ice, solid, no? Solid water, its specific heat is rather kind of small. No? I'll call it C sub I. No? C of the ice. Ice is half, no? 0.5 lang eh. No? So it's easier to heat up ice than to, no, heat up water, liquid water. No? But they are the same substances. No? For steam, steam is the gaseous form. No? Gaseous form of our ice, no? Of our liquid water. No? So let's call the specific heat of steam as C sub S. C sub S is similar to ice. No? It's equals to 0.5. Okay, so these are the specific heat. No? So we are talking here of the specific heat. No? So we have solid water, we have liquid water, and we have gaseous form of the water. No? Now for our Q1, no? So Q1 is raising the temperature of ice, no, from -5 to 0 degrees Celsius. So how much is that? How much will be our Q sub 1? No? So if you are to calculate Q sub 1, how do we get the value of Q1? No? Q1 will be the mass of the substance, which is 200 grams, no, times 0.5. 0.5 is the specific heat of ice. No? Its change of temperature is from -5 to 0 degrees Celsius. So that will be 0 minus -5. No? Nga 0 minus -5 because final minus initial. No? So negative of -5 will become +5. No? So +5 will be multiplied to another 5. No? So that will become 25. No? 25. No? So that's 0.25, I think. Okay, can you get Q sub 1 for me, guys?
500, sir.
Oh, 500 na nga decimal ni siya, no? 200 minus 0.5, that's already 100. Yeah, no? Tama, 500, no? So that will be 500 calories. Thank you, no? Okay. What is another form of heat that will need a change in temperature? No? So Q3, no? Q3 will also need, no, a change in temperature. So that's mass, no, which is still the same, no? Wala man na yan nag-ilis ang tubig just because it melts, it is still 200 grams man gyapon, no? So 200, no, times the specific heat of water, liquid water, times its change in temperature from 0 to 100, no? So again, boil siya naton. So it was increased, no, from 0 to 100. So 200 times 100, so you'll have how much? What is our answer here? 20,000.
1,000, sir.
So that's 20,000 calorie. No? So you'll need 20,000 calorie to boil the water there. No? Now, wala natin ginsolve ang Q sub 2. No? Q sub 2 is quite different. No? So this is a temperature when water remains at 0 degrees Celsius because it is melting. No? So from ice to complete liquid water, hindi na magsaka temperature yan. No? No change in temperature there will happen. No? So how do we calculate the heat absorbed for Q sub 2? No? If Q sub 2 is not the same, no, as our Q1, no? So for our Q sub 2, mag-solve tayo sa Q sub 2, no? Q sub 2 is actually equals to MLF lang, no? And LF is our latent heat of fusion, no? So this is still 200 grams of ice, no, that is about to melt. And the latent heat of fusion for water is 80 calorie per gram, no? Tama na ang LF natin, no? So 200 times 80, no? So that's 16,000, no? Calorie, no? So that's the heat needed for it to melt, no? Without changing its temperature, no? So we did not calculate Q sub 2 earlier because it has a different way of solving, no? So again, for water, no, the LF value or latent heat of fusion is 80 calorie for every gram of water, no? For steam, no, for boiling water, no? So for changing water into steam, no? The LV value, we call it as latent heat of vaporization, is 540 calorie per every gram of our substance, no? And now, no, our Q sub 4, that's the how we solve Q sub 4, no? Q sub 4 and Q sub 2 are quite similar, no? Except that they don't have the same latent heat of fusion value, no? So Q sub 4 is MLV, no? And MLV is still 200 grams, no? Times 540 calorie per gram, no? And medyo dako ni, no? Because it will have you will have to split the boiling water and make it into a gas, no? So that's 200 times 540. So you'll need a huge amount of energy there. That's 108, no? 1,000 calorie, no? Muna kadako nga heat yun kinanglan mo, no? To be able to make it into a gas, no? Na mag-evaporate, no? Now Q sub 5 is our heat, no, needed to increase the temperature of our steam, no? Now ang steam natin hindi na magsaka ang temperature ya until all of it, no, becomes steam. If there's still water there, liquid water, then hindi mo na mapasaka temperature yan, no? So the value there is still MC, no, delta T, no, which is still 200 grams of steam, no? But the specific heat of steam, as you realize from this end, no, is 0.5, no? So 0.5, and then the temperature now is 105 minus 100, no? Okay, so ang aton base temperature now is not all the way to 0, but 100. Kaya mo na niyang iyang temperature kaina, no? From 100 to 105, no? So that's 5 times this, no? So I think this is also equivalent to around 500 man, tama? And then therefore, no, how much heat was actually used up, no, to boil or to change ice, no, from -5 to 105. So we will add up all the values of Q. So Q1, which is 500, no? So this value is 500 plus, no, Q sub 2, 16,000. Q sub 3, which is 20,000, yeah, 20,000. Our Q sub 4, which is 108,000. And Q sub 5, which is not much, no, 500 lang. So our total value is how much? What's our total value now? So you have 500 plus 500, that's 1,000. Plus 16,000, no? Plus 20,000. So you have 37,000 calories. That one looks so big, but actually we can make it smaller by changing it into a kilocalorie. No? So if you make it into a kilocalorie, then that's merely 37 kilocalorie, no? To make it a little bit shorter. No? So this is the whole amount of heat needed now to convert ice into steam. No? Okay, so when we reverse the process, if you have a steam and you want to make it into an ice, you will also need 37,000 calories, no, for the material to give off. No? Once the material gives off that much of heat, then it will change itself into